All right, everybody, what's up? This video, we're going to look at vectors. All right, so let's go ahead and get started. So it says the term vector indicates a quantity such as displacement, velocity, or force that has both magnitude and direction. All right, and here we have two vectors. We have vector v and vector u. Now, a vector, it has an initial point called the tail, and then it has a terminal point, and we can call that the tip. And you can see that these two vectors here, u and v, vector u and v, has the same length and the same direction. Now, they may not look like it on the screen, but they are the same length. Okay, vector u and vector v are equivalent or equal. The zero vector has length 0. All right. Now, the way that we represent a vector, so you'll see it in textbooks and, maybe on the internet and your homework and stuff, like to represent vector v, they would do it like with a bold letter, okay? But, it's hard to draw bold letters. So what we do is we just draw say V, and then we can put a arrow over it. And you may see it with like a hat, okay? But I do it with the arrow above the letter, and that represents a vector. And another way that we could represent this vector v is we could represent it as vector AB. You have the initial point to the terminal point and put the arrow over it. Okay. All right, so let's look at this definition of vector addition. So if vector u and v, vector u and vector v are vectors positioned so the initial point of vector v is at the terminal point of vector u, then the sum vector u plus vector v is the vector from the initial point of u to the terminal point of v. Okay, so this tells us how to add vectors, how we can draw it. So let's we read all that, but let's do an example and let me show you what it looks like. So to do this, all right, so we have vector A right here. So what I'm going to do is I'm going to draw A. I'm going to draw vector A right here. Okay, and it may not look like it's going in the same direction or the same length, but it is. Okay, this is vector A right here. Now, what does it say to do? It says to put, okay, so we're looking for the sum. So we're looking for A plus B is what we're looking for. All right, so what we do is we take the initial point of vector B and put it at the terminal point of vector A. So I'm going to take this initial point and I'm going to put it right here, and we'll draw the vector. Okay, and this is vector B. All right. So it may be a little bit shorter than that. I don't know. It's going to look something like that. Okay. Now, the sum A plus B, what did it say? It's the initial point of A and the terminal point of V. So the sum A plus B would be right here. And I tell you what, let me draw that in a different color. So there's the sum A plus B. Okay, so that's one way that you can that you can represent a sum when you have two vectors. You just place the initial point of this one at the terminal point here. Okay, so we place the initial point of B at the terminal point of A, and then the sum is the initial point of A to the terminal point of B. All right, so there's another way that we can do this, and it's called the parallelogram law. All right, so the way that we would do that is, let's draw vector A. It's right here. And then, so what we do here is we take the initial point of B and we put it at the initial point of A. Okay? And then what happens is you create a parallelogram like this. And the sum A plus B is the initial point to where those two lines come in contact. And this would be your A plus B. And I mean, yes, this is exactly this. Okay, it may look off just a little bit, but that's what you get when you draw it by hand and you have no scale or anything. But that's how you represent addition of vectors. Okay. All right, so let's look at this definition of scalar multiplication. All right, so if C is a scalar and V is a vector, then the scalar multiple C times vector V is the vector whose length is C times the length of vector V, and whose direction is the same as V, so the direction will stay the same, if C is positive, and is opposite to V if C is negative. So if you multiply a vector by a negative number, it's going to go in the opposite direction. It'll still have the same length, but just the opposite direction. If C equals 0 or vector V equals 0, then C times vector V is equal to 0. And I need to clarify this. This right here would be vector V is equal to the 0 vector, and this would equal the 0 vector. Okay, I think we mentioned the 0 vector earlier, and this is how you would represent it. Okay. All right. So now let's look at what they're talking about on scalar multiplication. So here we have vector V. That's what we're going to base everything off of, this vector V. So if I do 2 times vector V, what it's going to do, it's going to go in the same direction. It's just going to double the length. Okay? And if I do half of vector V, same direction, it's just going to be half the length. Okay? Now this one, negative V, well, this is going to have the same length as this one, but you can see we're going in the opposite direction. And then if we have negative 2 times vector V, it's going to be twice the length of V, but going in the opposite direction. Okay? And that's what they were talking about up here when they were talking about C being positive and C being negative. Okay? All right, so let's look at this. So it says if A and B are vectors, draw vector A minus 2 times vector B. All right. So let's see how we can do that. All right. So the first thing is we have vector A minus 2 times vector B. Now, what I would suggest when you're drawing these things is I would change this to an addition problem. So I would say this is vector A plus negative 2 times vector B. So we're going to be adding these two vectors. All right. So now we have vector A. So let's draw vector A. All right. So there's A. Now we need to add -2 times vector B. So let's just come over here. Here's vector B. So -2, that would be twice the length, but in the opposite direction. So this would be -2 vector B. All right. And so how do we add vectors? Well, we can take the initial point of this one and put it at the terminal point here. And so that's going to look something like that. And so my solution would be the initial point of A to the terminal point of -2 times vector B. And this is our solution here. This is A minus 2 times vector B. All right, so hopefully all of that makes sense. Okay. All right, let's continue on. So now we've got components. If we place the initial point of A, okay, at the origin of a rectangular coordinate system, then the terminal point of vector A has coordinates of the form A1, A2, okay, and here's the pictures down here. See, we place the initial point at the origin. See, place the initial point of A at the origin of a rectangular coordinate system. Then the terminal point of A has the coordinates of the form A1, A2. We move on the x-axis A1 units, and we move on the y-axis A2 units. Or it has coordinates A1, A2, A3, depending on if we're in 2 or 3 dimension. Okay? All right. So these coordinates are called the components of vector A, and we write vector A is A1, A2. Notice the angle brackets, and remember what this says. These coordinates are called the components of vector A. And so the way that we can represent a vector is vector A is A1, A2. We can write it in component form. And then we can have vector A is A1, A2, A3. And notice the angle brackets on that. And there's the picture of it. So hopefully that helps. All right, so let's look at this. So we have vector OP right here. Okay, OP. And vector OP is 3, 2. See, the initial point is at the origin and the terminal point is at 3, 2. So we can write vector OP, and notice the initial point and then the terminal point with the arrow over it. All right, so we can write this as 3, 2, just like up here. See what it said? It said if the terminal point is at A1, A2, then we can write this vector is A1, A2, but with the angle brackets. And that's what we did here. And vector OP from the origin to the point 3, 2, okay? So vector OP is going from the origin to this point 3, 2, and this is called the position vector. Okay, it's called the position vector. Now we've got some other, let's see, where was it? I knew I had written it down, but oh well. Well, let's just talk about this for just a second. All right, so let's talk about these other vectors on here. Okay, notice all of these vectors. Okay, comparing it to vector OP. See how vector OP, it goes to the right 3 and up 2? Well, look at this vector. It goes to the right 3 and up 2. And this one goes to the right 3 and up 2. So, so what we can do is we can think of these vectors as representations of the algebraic vector A, or the well, not A, but just I'm used to saying A when I do vectors, but we can think of it as geometric representation or algebraic representation, or a representation of the algebraic vector OP, which is 3, 2. Okay, so they're the same vector. Their initial point is just in a different spot, but they have the same length in the same direction. Okay. All right. And then here it is in 3 dimension. So we can call this vector A, which is equal to vector OP. We're just going to call it A. Is A1, A2, A3 is the position vector of the point A1, A2, A3. So this is your position vector. And so if we're given the point A and B, okay, so we have vector A here. So the X is going over A1 units, the Y is plus A2, and the Z is plus A3. All right. And the vector A with representation AB, okay, talking about this vector here, is the vector A is equal to x2 minus x1, y2 minus y1, z2 minus z1. Okay, so that's, that's if you're given these points right here. So what does that mean? Well, if they give you 2 points, say 2 points A, B, then vector A would be x2 minus x1, that would be this component, y2 minus y1, that would be this one, and z2 minus z1, which would be that one. That would be vector AB, or, if we want to just call it vector A. All right. So let's look at this. Let's look at an example. It says find the vector represented by the directed line segment with initial point A is 2, negative 3, 4, and terminal point B is negative 2, 1, 1. All right, so we would have vector A is equal to, now remember we've got the angle brackets here. So look, this right here, this is your x2, y2, z2, x1, y1, z1. And so that's just x2 minus x1, and that's going to be y2 minus y1. And then we've got z2 minus z1. And so that's going to give us negative 4, 4, and negative 3. And there's your answer. Okay. So that would be the vector that's represented by those 2 points. All right. Let's look at this. So what about the magnitude or length of the vector V? Okay. Is the length of any of its representations and is denoted by the symbol. Now let's talk about that for just a second. The magnitude or length of the vector V is the length of any of its representations. Okay, so that's going to go back up here. Okay, you know, wherever it is. Okay, the length of all of these are the same. So by any of its representations, and is denoted by the symbol this or this. Okay, I don't know how your teacher's going to represent it. In this video, I'll do it with just one line. So the length of a two-dimensional vector A with components a1, a2 is the length of vector A is the square root of a1 squared plus a2 squared. And then I wonder what the length of a three-dimensional vector is with components a1, a2, and a3. Well, vector A, left that off, didn't I? The magnitude of vector A is equal to the square root of a1 squared plus a2 squared plus a3 squared. So that's how we find the magnitude or the length of the vector. Okay. All right, and then we have adding and subtracting vectors and multiplying by a scalar. Now, we looked at this. We actually added, subtracted, and we multiplied by a scalar, but we did it graphically. Okay, we drew it. Well, how do we do it if we're not drawing it? We're actually finding the components of the vector. So if we have vector A as A1, A2, vector B is B1, B2, then A plus B is just A1 plus B1. That's this component. And then for this one, that's A2 plus B2. And then same thing for subtraction, A1 minus B1, A2 minus B2. And then to multiply by a scalar, you just multiply the scalar to each component. Okay? And then it's similar for three-dimensional vectors. So if we're adding these two vectors here, you just A1 plus B1, A2 plus B2, A3 plus B3. Same thing for subtraction, and then same thing for a scalar. You just multiply it times each component. All right. So let's look at this next example. We have quite a few things we need to find here. So if we have vector A is 4, 0, 3, vector B is negative 2, 1, 5. So we want to find the magnitude of A, or the length of A, and we want to find the vectors A plus B, A minus B, 3 times B, and 2A plus 5B. And that arrow there looks like it's over the 3 and the B. It's over the B. All right, so let's go ahead and get started. So let's find the magnitude of A. Well, that's easy enough, right? We want the magnitude of this, so it's just this squared plus this squared plus this squared. So that's 4 squared plus 0 squared plus 3 squared, and it's the square root of all that. So that's the square root of 25, which equals 5. And there's your answer. All right. Now, let's do vector A plus vector B. And this should be pretty easy for you. If you took trig, then you probably did that in trig or pre-calculus. All right. So let's look at this. We want to do A plus B. So that's just 4, 0, 3 plus negative 2, 1, 5. And so when we add those, 4 plus negative 2 is 2. 0 plus 1 is 1. And then 3 plus 5 is 8. And there's your answer. And then we'll do vector A minus vector B. So that's 4, 0, 3 minus negative 2, 1, 5. And you know, I know I'm writing the vectors again. Do you have to do that? I guess you don't. You could just go up here and look. But I would recommend just writing them down like this so you have them right there. And I think it might, you're less likely to make a careless mistake. So we got 4 minus negative 2, so that's going to be 6, 0 minus 1 is negative 1, and 0 minus 5 is negative 2. And then we have 3 times vector b, so that's going to be 3 times this vector, negative 2, 1, 5. And so we just multiply the 3 to each vector, to each component here. So that's going to be negative 6, 3, 15. All right. And then the last one is 2 times vector A plus 5 times vector B. So that's going to be 2 times 4, 0, 3 plus 5 times negative 2, 1, 5. Now, what we want to do here is let's multiply by the scalars first. So that's going to be 8, 0, 6 plus, and that's going to be negative 10, 5, 25. And so that's going to be 8 plus negative 10, negative 2, 0 plus 5 is 5, and 6 plus 25, that's going to give us 31. And there's your answer. All right. So far, this should be easy enough so far, right? All right, so let's look at this. All right, so we've got some more properties of vectors. So if A, B, and C are vectors in V sub n, whether it's 2-dimension, 3-dimension, and C and D are scalars, then A plus B is B plus A. Commutative property holds. The associative property holds. It doesn't matter if you add the first two and then the last one, or the last two and then the first one. Okay? And vector A plus the 0 vector is equal to vector A. And then A plus negative A, the opposite, well, that's going to be 0. And we've got the distributive property here. We can multiply each vector by that scalar. Or if we have the C plus D added together, we can multiply the vector to each one of those scalars. And then if we have C times D times vector A, that's the same thing. We can multiply the scalar D to A and then multiply C. And then 1 times A is just going to give us vector A back. All right. All right, so let's look at this. Look at these vectors, I, J, and K. So vector I is 1, 0, 0, vector J is 1, 0, 1, and vector K is 0, 0, 1. All right. So these vectors, I, J, and K, are called the standard basis vectors. They have length 1 and point in the directions of the positive X, Y, and Z axes. In 2-dimension, we define, well, I would be 1, 0, and J would be 0, 1. So let's just look at the picture of them. So here's vector I. If you remember from when we plotted points, let's see. Well, look at that. I didn't do that very good. I labeled those axes wrong. X and Y. How about that? Does that look better to you now? All right. So here's vector I. See, we're just going to go 1 unit, and then Y is 0, Z is 0. And then here, you can see we're going 1 unit on the Y-axis, but X is 0 and Z is 0. See, we're not moving this way or up or anything. And then here, see, we're not moving along the X or the Y-axis. We're just going to go up 1 unit on the Z-axis. So that would be the 0, 0, 1. Okay? Just know all of these are 1 unit here. And then here it is in 2D. This would be vector I. That would be, 1, 0, and vector J, the 0, 1. To those points. Okay. All right. So if vector A is equal to A1, A2, A3, then we can write vector A is equal to A1, A2, A3 with the angle brackets. All right, so remember how we represent a vector with the angle brackets. Now, this is equal to, okay, so let's suppose that we added 3 vectors together to get this. That would be what? What would that be? That would be A1, 0, 0, okay, plus 0, A2 plus 0 plus 0, 0, A3. Couldn't we could do that, couldn't we? Okay, because if we add these 3 together, we end up with this. See, A1 plus 0 is A1, 0 plus A2 plus 0 is A2, and 0 plus 0 plus A3 is A3. All right. So what I'm going to do now is I'm going to pull out an A1 out of this first one. So that's going to be A1 times 1, 0, 0 plus, and then I'm going to pull an A2 out of here, A2, that would be 0, 1, 0, and then plus, and then I'm going to pull out an A3, 0, 0, 1. All right. Now, what is this? Well, okay, so of course this is vector A here. So vector A is equal to A1 times this vector. Now, what is this vector? This is vector I, right? Remember from up here? See, vector I is 1, 0, 0. You know, I just noticed this. This should be 0, 1, 0. I'm sorry about that. Yeah, I had that vector wrong. I guess I was in a hurry when I was writing these notes down. So sorry about that. But yeah, 0, 1, 0. Not 1, 0, 1. I have no idea why I put that. All right. And so now we have plus A2 times, and this is vector J, and then plus, and then I've got A3 times, and then what is that vector? That's vector K. All right. So this is another way that we can write the vectors. Okay. We can represent, so in other words, we can represent this vector, instead of writing it like this, we can write vector A like this. Okay. All right, so let's look at an example. So if we have vector A is I plus 2j minus 3k, and vector B is 4i plus 7k, okay? And just real quick for fun, what would these be if we wrote the components? That would be what? 1, 2, -3. And then this would be what? 4, and there's no j, so that would be 0 and 7. Okay, that's all it is. You can go, going back and forth. All right, so let's go ahead and work the problem. So we've got 2 times vector A plus 3 times vector B. And by the way, this that I wrote up here, that's not part of the problem. That's not part of what we're doing to work the problem. I just did it just for your information so you could see that. All right, so we would have 2 times vector A. So that's going to be times this, 2j minus 3k. and then that's going to be plus 3 times vector b, so that's 4i plus 7k. All right, and now all we're going to do is we're going to distribute the 2, we're going to distribute the 3. And so this is going to be 2i plus 4j minus 6k plus 12i plus 21k. All right. So, you know, it's not bad. It's pretty easy. You should be catching on to this. And so then we just combine. So that's going to be 2 plus 12. That's 14i plus, and there's only this j, so plus 4j. And then this one, that's going to be what? Plus 15k. And there's your answer. So, you know, there's adding, subtracting would be the same thing, and you can see here how we multiplied by the scalar also. We had to do that in the problem as well. All right, so moving right along. So it says a unit vector is a vector whose length is 1. That's a unit vector. Its length is 1. For instance, I, j, and k are all unit vectors. In general, if vector A does not equal the 0 vector, then the unit vector that has the same direction as A is vector u is equal to 1 over the magnitude or the length of A times vector A, which is just equal to vector A over the length of vector A. That's the unit vector that has the same direction as your vector A. So let's work this problem. It says find the unit vector in the direction of the vector this. All right. So what do we need? Well, we need 1 over the magnitude, right? 1 over the length times this vector here. That's what we need. Okay. All right. So first thing we need to do is we need to find the magnitude of this vector. So that's going to equal what? 2 squared plus -1 squared plus -2 squared. All right. So hopefully you see how that works, because remember, this vector here can be written as 2, -1, -2. And how would we find the length of that vector? It's just that squared plus that squared plus that squared. So it's just the coefficients there squared. Add them together, take the square root. And so this is going to equal, that's going to be 9 underneath there. So that's 3. So the unit vector, so the unit vector is equal to 1 over the length, so that's 1 over 3, times the vector, so times 2i minus j minus 2k. And so we just distribute the 1/3, so that's going to be 1/3. That's going to be 2/3 times vector I minus 1/3 times vector j minus 2/3 times vector k. And this would be your unit vector that has the same direction as that vector. Okay. All right. So let me just show you that this, what did it say about the unit vector? It says a unit vector is a vector whose length is 1. So let's look at this. What would be the length of that? Well, that's the square root, and then it's just this squared plus this squared plus this squared. So that's 2/3 squared plus negative 1/3 squared plus negative 2/3 squared. Now this isn't part of the problem either. I'm just showing you that it's going to equal to 1. So this is what, 4/3? See that? Let's just write it out. That's 4/3 plus, I'm sorry, not 4/3. How about 4/9? That sound better? Plus 1/9 plus 4/9, which that's going to give me, what is that? 9/9, which is square root of 1, which is 1. Okay. All right. Last problem. This is our last example here. So let's see what we can do here. All right. So it says a force is represented by a vector because it has both a magnitude, measured in pounds or newtons, and a direction. If several forces are acting on an object, the resultant force experienced by the object is the vector sum of these forces. Okay? So if several forces are acting on an object, the resultant force experienced by the object is the vector sum of these forces. All right, so let's keep that in mind while we're working this problem here. All right, so let's take a look at our example here. So we have a 100-pound weight hangs from 2 wires as shown in this figure here. Okay, find the tension or force of vector T1 and vector T2 in both wires and the magnitude of the tensions. All right. So how would we go about working this problem? Well, we need to get the horizontal and vertical components of T1 and T2. Okay, we want to get the horizontal and vertical components. And we're going to write them in the IJ form. Okay. All right, so let's look at this. If I draw this, okay, now this angle's 50, so that tells us. Let me do this in a different color. So that's 50, and then we know this one is 32. That one's 32 degrees because this one's 32. Alternate angles. You know, when you got parallel line cut by a transverse. All right, so let's get the horizontal and vertical component of T1 first. All right, so I've got T1 is equal to what? Now, it's gonna be the magnitude of T1. Okay, so it's the magnitude of T1 times the cosine. Okay, this is going to be your horizontal component. Okay, times the cosine of what? Of what angle? Of 50 degrees, this angle right here. Now notice I left a little space here, and that's going to be negative. Okay, that's going to be negative. So you might be wondering, well, how is it negative? Why is it negative? Well, look at this. Let's see. Let's get this one. So if I take this angle here, that is actually that. If I go along the positive axis, that angle's 130. So we do 180 minus 50 is 130. So that would actually be what? Cosine of 130 degrees. But we want to keep it in terms of the 50 degrees because, and we're gonna put everything in terms of 50 degrees and 32 degrees. All right. So the cosine of 130 is equal to the cosine of 50 degrees, that's your reference angle in the first quadrant. But remember, cosine is what? In the second quadrant, it's negative. So that would be, cosine of 50 is positive, so we would have to do a negative to make it equal to cosine of 130. And so that's where that negative sign comes from. And then, and then that's times vector I. And then that's going to be plus. All right, so now what do I need? I need the vertical component. So that's the magnitude of T1, right, times the sine of our angle, 50 degrees. Okay, so you might be wondering, well, how come there's no negative in front of that? Well, because if I do the sine of 130, that's equal to the sine of 50, that's my reference angle, and this is positive, but also 130 is in the second quadrant, so sine's positive also. So that would just stay the positive, and then that would be times vector J. And then we're going to do the same thing with T2. So that's going to be what? That's going to be the magnitude of T2. And this vector is going this way, so that's going to be the 32 degrees. So that's going to be times the cosine of 32 degrees times vector I plus, and then that's going to be vector T2 times the sine of 32 degrees. All right. So there's the horizontal and vertical components of T1 and T2 that we found. We found the horizontal and we found the vertical components. And so here's vector T1, here's vector T2. Okay. All right. Now, we've got to do some solving now. So we have the resultant of vector T1 and vector T2 counterbalances and we'll call this right here, this vector here, we'll call that vector W. Okay. Now notice, here we've got up here we had the IJ form. Okay. But this one, we're not going to have an I component there. So remember, let me do it in a different color. Remember, you have your IJ component, or your IJ vectors. There's I, and there's J. See, this vector just comes straight down. So it's going to be what? The force is 100. So W, vector W, is going to equal what? Negative 100. Now, remember, this is 0, 1. This one's 1, 1, 0. But that's going to be 100, negative 100, J. It's just going straight down. See, this vector, if we wrote it out, would be what? 0, negative 100, which would be this right here, coming down, negative 100. All right. So what that means is we've got to have T1 plus T2 has to equal, it has to counterbalance, okay? So that's going to have to equal negative vector W, which is going to be 100J. All right. So we've got to take T1 plus T2 and set it equal to negative W. All right, so let's do that. So I've got T1, which is negative vector T1 cosine 50I plus T1 sine 50J. So there's vector T1 right there, plus vector T2. So that's going to be T2 times cosine 32 I plus T2 sine 32J, and that has to equal this 100J. Okay, that's what we've got there, right? T1 plus T2 has to equal that. So that's what I did. I put this in for T1, put this in for T2. All right. So what I want to do now is I want to group my terms together. So this is going to actually give me negative T1 cosine 50, and then that's going to be plus, what is that, T2, and that's going to be, and that'll be cosine 32 times I. So all I did is I took this and I took this and I pulled the I out. Okay, and now I'm going to put the J's together. And so that's going to be plus, and that's going to be T1 times sine 50 plus T2 times sine 32, and that's times vector J, and that equals 100 times J. All right, so I hope that's bothering me right there. Let me see if I can't draw that a little better. So that's T1. All right. So far, so good. All right. So now look at this. See, I don't have the I vector over here. Okay, this would be like if I wrote this, I could write it. You see that? So in order for these two sides to be equal, this right here in front of I has to be 0, and this right here in front of J has to be 100. And so I've got, let's see, that's going to be T1 cosine 50. I mean, now all it is like solving a system of equations. Plus, and then that's going to be T2 cosine 32, and that equals 0. And then we have T1 sine 50 plus, and then that's going to be T2 sine 32, and that has to equal 100. So we've got a system of equations here to solve. Okay, So what I'm going to do here is I'm going to solve this, I'm going to solve this one for T2. Okay, let's solve this one for T2. So if I solve this first equation here for T2, I'm just going to move this to the other side. So that's going to be T2 cosine 32 is equal to T1 cosine 50. All right. And so what is that going to give me? Well, this tells me that T2 is equal to T1 times cosine 50 over cosine 32. So you just divided both sides by cosine 32. All right. So now you might be thinking, well, so what? What good is that going to do? Well, now what we can do is we can take this, which is T2, and we can take this and plug it into here, and then you see everything is the length of T1. So we can solve for that. That's one of the things they were wanting us to find. All right, so now I'm going to take this right here, and I'm plugging it in for T2 right here. So I get T1 times sine 50 plus the length of T2, which is this. So that's going to be T1 cosine 50 over cosine 32, okay, times sine 32 times the sine of 32. And that equals 100. All right. So now we solve for T1 now. So let's see what we've got here. So I'm going to take this T1 and I'm going to factor it out. That's a common factor. So I've got T1. Whoop, we don't do the equals yet. So that's going to be sine 50 plus, and now what's that going to be? That's going to be tangent 32 times cosine 50. Does everybody see, you see where that tangent came from? Okay, sine over cosine's tangent. Remember that. And so now that's going to give me T1 is equal to 100 over, divide both sides by this, that's going to be sine 50 plus tangent 32 times cosine 50. And you punch all that in your calculator and you end up with 85.64 pounds. Okay, there's the magnitude of T1. All right, now what do we need? We need T2, don't we? We need to know what T2 is. Well, let's come down here and find that. So T2 is equal to, well, what's T2? Oh, well, look at that. It's this. You see this right here? We got T1, so we just plug this in right here. So that's going to give us 85.64 times cosine 50 over cosine 32. Punch that in your calculator. You get 64.91 pounds. Okay. That's the magnitudes of T1 and T2. Now, what else did they want? It says find the tension or force in both wires and the magnitude of the tensions. All right. So the tension, well, what is that going to be? Well, that's going to be for T1. All right. So we're finding the tensions now. That's going to be the negative. Now, well, let me tell you what I want to do here. Well, I don't know if it's all going to fit, but basically what we're doing here is, where are we? Okay, so let me erase this. So what we're doing here for the tensions is so remember this right here is T1, and this right here is T2, right? So what we're going to do is we're going to plug the values we got for T1 and T2. We're going to plug those into here and do that times cosine 50, and then T1 times sine 50, then T2 times cosine 32, and T2 times sine 32. Okay? And I don't know, I might be able to, let me grab this. Let me just see if I can pull this down here. Okay, so there we go. All right, so like I said, this is this is T1, this is T2, okay? So, I just put it down here so we can see it. So I've got T1 is equal to negative 85.64 times the cosine of 50 I plus 85.64 times the not cosine, times the sine of 50. All right, so I just took this number and plugged it in for T1 there. See, that's what it is. And so I get T1 is equal to, that's negative 55.05 times vector I plus 65.6 times vector J. So there's T1. And then T2, so I'm going to plug in the 64.91 in here and here. So 64.91 times cosine 32 I plus 64.91 times sine 32 times J. And that gives us 55.05 I plus 34.4 J. And that's what they were asking for. That's the tension, and this is your magnitude. All right. These are your tension vectors, and these are your magnitudes. All right, so that was kind of a long video. Wasn't too bad. That last problem took up a lot of the video, didn't it? So hope this video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see y'all in the next one. Later.